Magnetic coordinate systems. You use these to have your coordinate plane. And up here we have these are magnetic coordinate points, so you can place these on your coordinate system, as well as you can use your two color counters. If you had let's say Bristol board could have used these colored pins to represent coordinates as well, and these are some more colored pins over here. So if you notice here, these are magnetic on one side and they are colored differently on the other. And these are your markers. They are magnetic as well. One side is magnetic and this is your erasers. You can locate coordinates and plot them. Let's say you wanted to form a parabola. You can plot these points and form your parabola. And you can erase using this. And look at the magnetic surface. Here's the rest of the toolkit. We have here algebra tiles. These are our square tile, x square tile. This is our minus x square tile, or x tile, and our unit tile, negative unit tile, alright? And this is our positive unit tile. If you were to take a look on the magnetic board, the dimension here is x and here is x. The area therefore would be x squared. This is the x tile and this side is x, and this is 1. The area would be x times 1, x. So this is the x tile. This is the unit tile. 1 times 1 is 1. So this is 1 unit. Note the difference in the colors here. This is the negative x squared tile. This side is negative x. This side is positive x. The area therefore will be negative x squared. And this is the negative x tile. This side is negative x. This side is 1. Negative x times 1 is negative x. So this is the negative x tile. And this is the negative unit tile. Here is negative 1. Here is 1. The area is negative 1 times 1, negative 1. Hi, and welcome to my virtual manipulatives for teaching algebra. So this is my algebra toolkit. So when I click here, I have a range of algebra tools that are available virtually, and these are for free. The first one I look at is the algebra tiles, and when I click on that, I'm going to be launched into this platform called Polypad. Polypad is a versatile tool which has many different features, but I'm just going to look at the algebra feature for now. Here you can use the algebra tiles. Upon this section is the positive tiles, and the lower section is the negative tiles. So I can drag the tile over to, let's say, if I were to factorize. In factorizing, you need to just simply make a rectangle, and the rectangles, as you recognize, align with the side of the square, and the unit tiles aligns with the vertex of the square at this point, and so you would form a nice rectangle here. So this would be the factorization of x squared plus 3x plus 2. You would recognize that there is one x squared tile 3 x tiles
and the 2 unit tiles.
Hence the reason this factorizes to x, which is this side, plus 2, 1, 2 units into x plus 1. X is the length here, 1 is the length here. So when we find the dimension of the rectangle and we put it together in a binomial form, it represents the factorized version of this expression. Here's another tool in my toolkit. This is Desmos, and we can use Desmos for a variety of functions, but we'll use the Desmos to create some sliders. The sliders are very good for demonstrating the effect of changes in the coefficients of functions. So let's look at a function. Let's say a quadratic function. We're going to input, we're going to come up at this point here. You choose the sliders. This is the sliders, and let's put in a quadratic function. Let's say we have ax squared. To input the x squared, we bring up the pad here. Ax squared plus bx plus c. Alright, so here we have the function a, b, and c are arbitrary constant. I'm going to click all here because we want to see the effect of the change in the values of a, b, and c. Slide to the right, you would see the values increasing, value of a increasing. When you go to the left, the value of a is decreasing. Note carefully, we would have learned that when it is greater than 0, it's concave upwards. When it's less than 0, it's concave downwards. This can be great in demonstrating these facts, right? As well as you can move the constant all around, and you can see it's basically translated. All right, so this is one of the good things about Desmos. Now let's look at the equation balance. When I select this, it takes me back to Polypad because these are preloaded virtual softwares that I particularly selected. In Polypad, to get the balance, what we need to do is to select the scale. So the scale indicates that we're going to use the balance, right? Suppose I wanted to model an equation. Let me use some of the tiles from the algebra. I wanted to model, let's say, 2x. Let's do an easy one. 2x plus 1 is equal to 5. So I drag 5 unit tiles on the other side. But when we recognize you have created this particular equation, you would see that it appears to be unbalanced. Look at the inequality sign here. So what we have to do is we have to create an equality by clicking on this part here and click balance. So this is the equation we wish to create. So to solve the equation, what we do is remember to create a balance. Whatever I do on the left, I have to do on the right. So I created a 0 pair here. And since I created a 0 pair here by adding -1, I do the same on the left hand side. So you see here a balance is created. Now that a balance have been created, I can delete these two that the 0 pairs that were created there. And after deleting it, we would see that we'd have 2 here is equal to 4. What we do now is rearrange them so that we'd have a one-to-one correspondence. So we'd have one of the x corresponds to 2 unit tiles. We could get rid of this correspondence. So I delete here and delete here as well. Let's delete here. And voila, we have the value of x is equal to 2. Here's a popular software, GeoGebra. With GeoGebra, you can do a range of things in algebra, but let's first look at solving a simultaneous equation in which one is linear and the other is quadratic. Okay, so to input our values, we're going to come to this point here, put in our values. This is our keypad. We want to put here, let's see, x squared. Let's keep it simple. So we have x squared as one of the functions. And if we wish to add another function, let's say we're going to add another function here. And we're going to look at, let's say,
Y is equal to X. Here you would see the function Y is equal to X being demonstrated.
so you would recognize this is the function in green, that's the quadratic function. The one in red is the linear function. And to get the solution, what you can do first, you can magnify it. In magnifying, you would recognize that you would see the solution a little bit better. And of course, the scale changes as you magnify it. Then you can select your point and go to the intersecting points. That is at that point. And here's the other point. Scroll down. All right, so I select the point again. And if you observe carefully, the point here is B. Here's the point B, and it gives you the coordinates of B, which is the solution, x equal to 1, y equal to 1. And you notice here is A, and they give you the coordinates 0, 0. So these are your two solutions. As you would observe, there are a range of other tools in my toolkit, but the last one I would look at is the two-color counters. This is particularly used for teaching directed numbers. All right, okay, so we see here, right, it comes up. So let's say we wanted to model 3 minus 2. So if I had 3, I would have put 3 of these counters. These yellow ones are the positive ones. So that is 3 minus 2 means we're going to have 2 of the red ones. All right, so 3 minus 2. When they come together, the red and the yellow, they form 0 pairs. So this is equivalent to 0. This is equivalent to 0, leaving you with this, like a cheese that stands alone. So we have 3 minus 2 is equal to positive 1. Okay, let us look at another case. Let's say we had 5 minus 8. So let me rearrange this here. So we have 5, 1, 2, 3, 4, 5. Minus 8. That's 1, 2, 3, 4, 5, 6, 7, 8. Alright, so what we do, we create the 0 pairs. And let's create the 0 pairs. This pairs with that. This pairs with that. This pairs with that. This pairs with that. There's another software that is actually better. When you pair them, you actually see the 0 pairs, right? But for the sake of demonstration, we recognize these are paired, and so this is equivalent to 0. So your answer is the amount of tiles that remains by themselves. That is 3 red tiles, and these are the negative tiles. Your answer, therefore, is negative 3.